Okay, so let's build it. Section 13.2, line integrals, video 12, line integral of a vector field. All right, so I've got a setup here. We've got a vector field F, capital F, in R3, and we've got some curve in space that starts at a point P0 and ends at a point P1. How would we calculate the total work required to move a particle along this path when the force acting on the particle is calculated by our vector field? Remember, a vector field is just a function that takes a point and assigns a vector to it. So for example, at this point we might have a vector pointing that way, and then over here, and then the vectors may be turning and rotating, the force vectors. So let's see if we can figure out how to calculate the work. And I am going to go through the formal setup as much as I can without taking too much time. And the reason it's important to understand the formal setup that leads to an integral is when you're doing physical and engineering applications and applications in other science areas, there may be problems where you do not know how to set up the calculus. Well, calculus comes into existence by cutting things into little bitty pieces, adding up stuff, and then making the pieces shrink to zero and therefore adding up an infinite number of things. In other words, setting up a Riemann sum, and then when you hit it with the limit, it morphs into your integral. So it's important to be able to adapt to new situations and ask yourself, well, what would I do if I cut this into small pieces and I assume things like lines and right angles? Because remember, when you did the first integral in calculus, you started by cutting up the x-axis, or an interval in the x-axis, and then using something convenient like rectangles to approximate an area, and then take a limit, and then you get your definite integral. Same thing here. The trick is to cut into pieces that act predictably. Usually that means right angles and straight lines. So let's see if we can do this here. Let's say that we partition this arc into some pieces, and let's take a couple of them here. Let's take this piece and this piece, these partition points, if you will. Let's call this one Pi minus 1. This would be consistent with the textbook on page 768. And we'll call the next point where we partition Pi. And let's see if we can estimate the work required to move a particle from Pi minus 1 to Pi. If this is a small enough arc, we can estimate the path with the line segment. So let's say that the direction that this path is going is, let's see, well, how can we estimate that vector? Well, if we move it up a little bit, it's almost the tangent vector. In fact, the tangent vector is a good approximation for the path if the path is short enough and linear enough. So the direction is approximately, well, we know the direction it goes. Let's take the unit tangent vector. But is that necessarily the magnitude of the vector? Well, not necessarily, because if the magnitude of this vector was 1, this distance may or may not be 1. So how can we estimate that distance as a scalar to have the correct length of the tangent vector that's pushing it so far? Well, we can estimate the distance between the two by just multiplying it by the arc length, or the changing arc length. Now be careful, this is a vector, this is a scalar. So really, it would look a little bit better if we said delta S, this scalar, times that unit tangent vector. So the tangent vector, it is unit. The unit tangent vector to say this is the correct direction, but this has a magnitude of 1. To push it far enough, in other words, the change in the arc length, we would have to multiply that vector times how far we want it to go. All right, so what about the force acting on this point? Well, the trick to estimating the force is to pick some random point in that small sub-arc, and we'll call this random point xi star, yi star, zi star. So we know the direction it's traveling, or we have a displacement vector to represent the direction it's traveling. In order to calculate the work to move it across that arc, we need to multiply it by the force vector, and that's where the vector field comes into play. So the force acting on this particle is approximately the vector function, the vector field evaluated at the point xi star, yi star, zi star. And to be fair, for the unit tangent vector, I should also indicate that we're going to substitute the same xi star, yi star, and zi star. So we have to pick a point in there to represent the the displacement vector, at least the direction of it, using the unit tangent vector. And then, of course, times the arc length so that that vector pushes the point far enough. All right, so on this subarc, we have a force vector thanks to the vector field, and we have a displacement vector thanks to the unit tangent vector, multiplied by the arc length. Again, that's to push it far enough. If we don't put the delta s, then that tangent vector would only push it 1 unit, but we need to push it the distance of this arc, roughly. So delta s is the length of that arc. So now that we have the force vector and the displacement vector, we can set up an expression for the work. I just thought I'd just open that black marker. Maybe it's this one. Then the approximate work required to move a particle from pi minus 1 to pi. I left out an important sentence, so I'm going to pause and fill that in. Luckily, I have a little bit of space here. Partition the path at P0, P1, Pn. So I didn't label all the points where we partitioned it. P1, P2, the last one would be Pn. Actually, I shouldn't say P1 because we're calling this P0. What should we call it? Actually, yeah, I can call this P1, but that's called P1 also. I need to give that a different name. Well, we'll just call it Pn, because I call this P1 with the partition of the arc. But regardless, don't let the notation bog you down. We're cutting up the arc into a bunch of pieces. But let's partition the path at P0, P1 all the way to the last point. So we'll change this to n. Then the approximate work required to move a particle from one partition point to another is the work is equal to the force vector times the displacement vector. So the vector field evaluated at xi star, yi star, zi star dot delta s times the unit tangent vector evaluated at xi star, yi star, zi star. All right, so we cut into little bitty pieces, find what we want for one of them, in this case the work. Then we add them all up to find the approximate work for the total thing, and then we take a limit. So the total work to move a particle from P0 to Pn is, the total work is the sum, and I'm going to go back up here to where I wrote W equals and put Wi to mean the work required to move the particle along the ith subarc. The total work is approximately, and if I'm going to say approximately, I should use the wavy equal sign. The sum from I equals 0 to n of this expression. Now, one thing I am going to do in order to make the transformation from Riemann sum to integral complete is I'm going to take advantage of a property that in my calculus and linear algebra classes I call scalar fluidity. If you have a dot product and there's a scalar on one of your vectors, in this case the second one, the scalar is fluid in the sense that you can move it to the first vector, you can move it to the second vector, or you can wait until the dot product is done and then stick it at the end. I'm going to move this scalar to the end after the dot product gets completed. So we have the force, the vector field evaluated, which is the force, at xi star, yi star, zi star, some random point picked on the ith arc, dot the unit tangent vector evaluated at that same point, xi star, yi star, zi star. And now I'll close off that expression and throw the scalar at the end, the delta s, because this is just screaming Riemann sum now. Therefore, the actual work done is we take the limit as n approaches infinity. And I need to be careful here. This is not technically what we should say. What we should say is the limit as delta s approaches 0. And actually what we should say is the limit as the maximum delta x approaches 0. We can't just say n approaches infinity, because I could take these, I don't know, looks like a dozen partition points, leave the first, all but one of them in the same place, and in this last subarc, cut it into an infinite number of pieces. So in that case, we're getting an infinite number of partitions, but these are all still pretty long. And I can't just say delta s approaches 0 because there's a bunch of them. So we'll say the largest arc length approaches 0. That forces all of them to approach 0. So the actual work is the limit as the largest arc length approaches 0 of that sum, which I'm not going to rewrite, it's over there, which by definition is the line integral over the curve C. I didn't call it C, but it's this curve, of that expression, the vector field dot the unit tangent vector ds. And this is how you evaluate the line integral over vector field. There are a couple of other representations of that, which we'll see in the next video, because I think this one's gone kind of long, and we'll also do an example.